extending Taylor's theorem, we can see that these polynomial approximations are not only really good at estimating the values of some of these functions, but that in certain cases that if we write enough terms, or we think of if we are able to write out an infinite number of these, or create an infinite series out of this Taylor process, that we'll actually not only get something close to the function, we'll get exactly what the function is. So the second part of Taylor's theorem says that a function is exactly equal to its infinite Taylor polynomial better known as the Taylor series, if and only if this condition is met. And the condition is that the error, or the remainder in this estimation process, disappears or shrinks to zero if the limit, as we add more and more terms of this remainder centered at C, is equal to zero. So if the error term, by adding more and more terms, if the error becomes zero, then this polynomial is in fact not just close to the function, not just a close approximation, it really is the function. It's an alternate way to write the rule for the function. And this turns out to be very useful in situations for being able to represent functions we didn't know how to represent before, such as like we saw in power series, how to represent a function like e to the x, or sine x, or cosine x as a polynomial. It turns out that those aren't actually good estimations. They're exactly what the series is equal to. So here's an example of doing just that. This time we're like the function fx equal to the natural log of 1 plus x, and we'll find a Maclaurin series for this. And we'll also show that it's equal by showing that this is not only an approximation, but it's in fact equal to this infinite series, because the remainder term in fact tends to zero. Its n tends to zero. Let's see. So if we're going to write a Maclaurin series, we better be able to come up with kind of a rule for how we're creating terms in this polynomial along the way. And it's not exactly clear how to do it here, so maybe we'll collect some data. We know if we're going to write a Maclaurin series, or a series centered at 0, then we need to know the value of this function at the center. Natural log of 1 plus 0 is natural log of 1, which is 0. We need to know what the first derivative of this function is. The first derivative of natural log of 1 plus x is 1 over 1 plus x. So the first derivative at the center is 1 over 1 plus 0, which is 1. Second derivative, this is 1 plus x to the minus 1, or this is minus 1 over 1 plus x to the minus 2, or squared. So the second derivative at the center is negative 1 over 1 plus 0, or negative 1. The third derivative, bring down the minus 2, and this is equal to 2 over 1 plus x to the minus 3. So the third derivative at the center point is 2 over 1, which is 2. It's not quite clear what the pattern of these derivatives is, so I'll find a couple more. The fourth derivative should be 2 times minus 3, or minus 6, over the next power of 1 plus x. So the fourth. So that means the fourth derivative at the center is negative 6 over 1, which is negative 6. Okay, that was interesting. Let's try one more here. Maybe not quite positive what's happening here. The fifth derivative should, let's bring down the minus 4, so -6 times minus 4 is positive 24, plus x to now the fifth. That means the fifth derivative at the center is positive 24. I've seen these numbers before. This is -1. This is the next one is just the previous term times 2, times 3, times 4. This is 4 factorial. This is minus 3 factorial. This is 2 factorial. This is minus 1 factorial. This is minus times 1 factorial. This is 0 factorial, and this is just 0. So I think it looks like this Maclaurin series that approximates natural log of 1 plus x is 0, is strange. The Maclaurin polynomial is 0 plus 1 over 1 factorial times x plus minus 1 over 2 factorial times x squared plus 2 or 2 factorial over 3 factorial times x to the third plus minus 6, which is minus 3 factorial over 4 factorial times x to the fourth, and so on. I think the pattern I'm noticing is that I think if I want to write the x to the nth term, that's going to be, well, n minus 1 over n factorial. Looks like the exponent and the denominator match up. The top is a factorial of 1 less, so that's going to net me at 1 over n. And it looks like the sign is alternating, where when the exponent is even, it's minus. So I think that means we want a minus 1. Evens are negative, so it should be off by 1. So in sigma notation, I think this is saying that this Maclaurin polynomial is the sum from n equals 1 to infinity of minus 1 to the n plus 1 over n times x to the n. We'd like to now show that this is actually not only these estimations are the Maclaurin series, but actually they're dead equal because the remainder happens to be exactly 0. So we need to be able to calculate the remainder term of this after n times. So let's see, the nth remainder of x centered at c, in this case since Maclaurin, c is 0. That should be, according to my definition, the n plus first derivative when I plug in some z that's between x and 0 over n plus 1 factorial times x to the n plus 1. I'd like to get an expression that this remainder is definitely less than, and we'll try to look at its limit. With any luck, the limit of this new estimation that we can actually calculate will tend to 0. And again, note that z is between x and 0, or namely 0 is less than z, which is less than x, which is, according to our domain, less than or equal to 1. Further, because of that, I'd like to state what the n plus first derivative is. From looking up here, the n plus first derivative seems to be n minus 1, or 1 less than the derivative I'm at, factorial on top, and then a 1 plus x to the power of whatever derivative I'm at. So I think the n plus first derivative, when I plug in z, is going to be n factorial over 1 plus what I plugged in, z, to the n power. There is an alternation here, but since I'm going to be doing this in absolute value, I don't really care about that minus 1 to a power. So the absolute values will take care of that. So put this together. I'll substitute, let's replace what f is in here, and let's get something that we can get a better handle on. This tells me that the nth remainder of x centered at 0 is really n factorial over 1 plus z to the n plus 1 times n plus 1 factorial times x to the n plus 1. So a couple things. I know that n factorial divided by n plus 1 factorial is just 1 over n plus 1. Also, because of where z and x live, z and x are both smaller than 1, or at most equal to 1. I know that this power is definitely smaller than 1. So if I replace it with a 1, it makes this term bigger. Similarly, since z is a positive number, 1 plus something, 1 point something to various powers gets bigger. And as denominators get bigger, expressions get smaller. So also, if I replace this with a 1, I'd make the denominator smaller, which would only make the remainder term even bigger. So I think that putting those two lines of reasoning together, that I think that this remainder term is definitely smaller than if I replace this value, this x to the n plus 1, and this 1 plus z to the n plus 1 with 1s. That just makes this remainder term bigger. I think that's smaller than n factorial over n plus 1 factorial, which is 1 over n plus 1. So, what does that mean? So, what's the limit as n tends to infinity of this remainder term? Well, this limit is definitely smaller than the limit as n approach infinity of 1 over n plus 1. 1 over n plus 1 tends to 1 over, as n tends to infinity, tends to 1 over infinity, which is 0. And moreover, note that the remainder term is absolute value, and the smallest absolute values ever get are 0. So by the squeeze theorem, this remainder this limit of the remainder is itself 0. Therefore, the Maclaurin series is actually equal to, that we wrote down, is actually equal to the function.